let me continue now after the break. So now we're going to look at another example of using ports. And this one is a simpler technique, which is removing sequential dependencies. So let me go to the slides first and show you what I'm going to do. So this is a technique that you can use in many programs to make them more flexible. So if you look at a sequential program, basic idea is that all the instructions are executing in order. That's clear. Huh? So there's a dependency. So they will go one after the other. So a later instruction can only execute if the previous one has executed. But that might be a problem. Sometimes it can introduce a useless dependency. Maybe one of the instructions blocks for some reason, variable, unbound, whatever. And so the later instruction cannot execute. But maybe that's kind of a useless block. Maybe those two things are not related, and there's no reason for the second one really to wait for the first one. So this is a useless dependency, and maybe we want to get rid of that. Okay? So now we can add new threads, and we can remove dependencies. So we can use what's called concurrency for dummies, okay? And to remove some of these dependencies. Now this doesn't always work. So here is, so we will need a port to collect the results. So here's an example of a function called filter. It's a standard kind of a functional program. You have a list L and a one-argument Boolean F, and you will only output the elements for which f of x is true. Okay? So this is a typical kind of functional abstraction that we're going to use, that can be used a lot, but it introduces dependencies. Okay? It introduces kind of useless dependencies. So here's an example. If we do filter A51B406, and the function is testing whether x is greater than 2. So the A is an unbound variable here. Why is it unbound? Well, it might be computed by something else. Maybe we don't know it yet. So there's some wait we could have to do here. But this filter function will block on the A right away. But actually, that's kind of annoying, because 5, 4, and 6 are already in the list. And we know they're going to be in the output. We know that 5, 4, and 6 are greater than 2. They're going to be in the output. But we won't calculate that yet until A is bound. So the unbound A introduces a dependency. So waiting for A stops everything. And also the 1 and the 0, we can also immediately eliminate them. They won't go in the output. We can already know that without waiting for A. So this is a problem. So let me define the filter first with this problem, and then we'll fix it. So is that clear? The filter function is actually a quite simple function. Huh? So let me go now to the code. So here, let me define a filter. Declare function filter LF. So this is, again, is a higher order function. Case L of H bar T. If f of H, then H goes to the output. H filter TF. Else it does not. Filter TF with no H. And then we have the nil case. So this is a simple filter function, and it does the right thing. Okay. We can do something like browse filter 1, 2, 3, 4, 5, And here's a simple function, x greater than 2, and it prints 3, 4, 5. That's clear, greater than 2. But if we have variables in there, filter A, 2, 3, 4, 5, fun, we have the same as before, but now we have this A, which is unbound. So what is this going to display? Think about it. When I feed this, what will you see here on the left, in the browser window? You will actually see nothing, because the main thread executing filter and browse will block inside of filter. It's this A here. In fact, where will it block exactly? It's when the function tries to do A greater than 2. So the greater than operation here inside filter, so here, will block when it sees an unbound variable. So that's exactly where it's blocking. So I run this, and nothing is displayed on the left, nothing at all. And I can get everything to display by doing A equal 1. Bing, and then I see 3, 4, 5. So everything is stopping because of the A, which is kind of a pain. Okay, so you see that, and you see maybe we want to keep running even though some of the variables might be unbound. We want to remove this dependency. Okay, so let me show now how we can do this. So let me go back to the slide. Okay, so waiting for A stops everything. So we want to get rid of that problem. Okay, so we want to write a new version of filter that doesn't have this problem. We will write, and I will call it ConcFilter, concurrent filter. We will build a new version of filter, and we'll use 2 building blocks. So I'm going to use the concurrent composition. So I'm going to actually use barrier in there to make it work. And I will also use ports, so asynchronous channels. Those are the 2 building blocks we will use. But ports with a close operation, which adds nil to the end. So far, when we used ports for streams, we never closed the ports. But now we want the port to close the stream, to make it a list, to put nil at the end. So we'll have ports with a close operation. With this, we can write ConcFilter, and this, when I run it on this list, A51B406, it will immediately return 5, 4, 6, and then wait for further. And it will immediately eliminate the 1 and the 0, so it doesn't have to do the computation anymore. But the problem, though, this is going to work fine, but introduces another issue. These elements will be returned in any order. Okay, the 5 will be returned before the 4 and before the 6, but not always, because they will be running in their own threads. You see, we remove dependencies, we make things independent, but independence equals concurrency. And concurrency means we don't know the order. So there's an automatic trade-off here. When we remove sequential dependencies, we introduce independence, which means concurrency, which means non-determinism. Okay? So there is an essential trade-off between removing dependencies and non-determinism. So because of that, these elements actually could come in any order, 6, 5, 4. And also it depends on when the variables A and B are bound. If A is bound later than B, then the B will output first. If A is bound first, then the A will first. So we will introduce this non-determinism. Okay? So that's unavoidable. So if we want filter to be deterministic, then we have to accept sequential dependencies. But in many cases, we don't care about the order. We may not care. It's not important. And then we can remove dependencies. Okay? So in order to do that, we need to define ports with a close operation. We define ports where we have a send to the stream. So S is the stream, the send, and close, which will bind the tail to nil. So this is an extra operation. So far, when we used ports, we didn't do close because the stream is going on forever. But here we will need to close it. So actually, I will have defined this for you using a cell. So a cell is like an object attribute. It allows reading and writing, assignment. So I'm not going to explain completely how this works, except that I create the cell, and the cell is like a variable that you can assign and update, like an object attribute that we saw in the passive objects. And the cell will always contain the end of the stream. The send will add, and it will use an operation called exchange, which does both read and write in one operation. So the exchange will bind old to this argument, which is ms, and the new one will be this. So the exchange reads the old value and updates. So exchange see old new is like this. It's like old is equal to the result of C, the value of C, like an attribute, and the C will get the new. But this is done together. It's atomic. That means the scheduler is not allowed to stop in between. For the scheduler, this is one operation. The scheduler will do everything or nothing. So this is called an atomic operation. The scheduler cannot break it into two. So with this, we are guaranteed that the send will always work correctly in concurrency. Remember the errors for the passive objects? Remember we had a problem with increment? Well, using exchange is one way to fix that problem, making things concurrency safe. So using these ports, we can define ConcFilter. But let me now write the code for this. If this is, so there's a question, if there's a cell, this isn't functional programming anymore. You are completely correct. We are using the cell to implement a port, and anyway, a port is not, ports are not functional, and cells are not either. You are completely correct. This is no longer functional, and in fact, ConcFilter is non-deterministic. So that means it's not functional anymore because the results can change the order. It's not always the same result. You see the trade-off we're doing, huh? Where you remove dependencies, we introduce non-determinism. So we're actually leaving the pure functional environment. In this case, maybe it's okay. Maybe we don't care about the order of the results to filter. Okay? If we don't care, then we are allowed to relax a little bit the functional because we want to remove dependencies. You see, this is a trade-off. When you make your own programs, you have to decide, do we want to keep it completely deterministic and functional, but you might have extra dependencies if you do that, or can we remove these, are we allowed to remove these dependencies, but then it maybe becomes not functional. Okay, that's completely right. So let me go now. First, now we will define ConcFilter, but first we will define ports with close operation because we will need that inside of ConcFilter. So a procedure, so new port close. We have a stream S, we have the send operation, and we have the close operation. Okay, so we will create a port. So let me call it, we'll create a cell, sorry, which contains the end of the stream. The S is the tail of the stream, always, okay? It starts out by being S, but when we bind it, it will move on forward. And then we define the two procedures, send and close, okay? So basically that's how it works. Let me now fill in the blanks here. So the send is going to do an exchange operation. It's going to read the old value. So we'll need to get a new local variable. So we will bind the old value to m bar s. So this actually extends the stream. And then it will set s as the new value of the end of the stream. So this is actually doing exactly what the send of a port should do. And then the final close operation will actually, sorry, I have to make the name of the cell here. And close will actually bind the end of the cell to nil. But once you do a close, you're no longer allowed to do sends anymore. So this will define a port with a close operation. So let me now give an example of this. New port close, S send close. So this will create a new port. And let me browse S. So S is an unbound variable, of course. I can do send A, puts A there, send B, puts B there, and if I do close, sorry, with a capital C, it will bind to nil and it's done. Okay, so with new port close and barrier synchronization, we can define the ConcFilter. Okay, is that clear for everybody? So let me go back to the slides now and show you, explain how the ConcFilter is going to be defined. So we have now ports with a close operation, so we can define ConcFilter. So here's the idea for ConcFilter. So let me compare ConcFilter with the original filter. So filter LF all these fx will be done in the same thread. So ConcFilter LF will run each f of x in a separate thread. So that's the main difference. Each f of x will be run in its own thread. So if x is unbound, then it's that thread that will block and the main thread will not block. Okay, so if fx returns true, then we send x to the port and x appears on the stream. Okay, and the port stream will be the function's output. And when all the threads terminate, we close the port. This is why we need barrier. Okay, for all the elements in the input list, we run a thread, but we have to know when it's all done because the output has to be a list. There has to be nil at the end. So we use barrier to detect when all the threads have terminated, and then we will do a close. Okay, so barrier has procedure arguments, PS, so we have to create these procedure arguments. Okay, so for each x in the input list, we have to execute this. Okay, and barrier will create the threads. Okay, so for each x in the input list, we have to execute if f of x, then send x end. So the argument to barrier will be this procedure. Okay, it will be proc $ if f of x, then send x end end. So we have a list of those procedures. So again, we're going to use higher order programming to build this. So here's the definition to ConcFilter. So again, this is a very nice example of a higher order combinations of things we do with higher order. So you see how it works. We have one call to new port close. We have one call to barrier. Now I'm writing this as a procedure because I need to access the output. So you see the usefulness of the kernel language now. A function is just a procedure with one extra argument. We need the L2 because that output is actually the stream of the port. Okay? So we need to access the output. So first we create a port, new port close, and then we do barrier. Now barrier takes a list of procedures. So we will compute this list. We will compute the input to barrier. So we will do a map here. For each element of the input list, we will build a procedure. So this in the red box is the procedure. So this function will be run on every element of the input list, and it will output this procedure. Okay, which is if f(x), then send x end. So this is the procedure that is going to be part of the input to barrier. So you see, we actually will construct the list of procedures that is the input to barrier. Note, again, this is an extremely higher order, and this is a very dense program. We're actually doing very powerful manipulations, okay? And so then barrier will do the rest of the work for us. Barrier will create a thread for each of these procedures, and it will synchronize on all of those threads being done, okay? So let me write now the code and show you how it works. So again, let's see if anyone has any questions. Again, it's important to study carefully how ConcFilter is written, because it's a really interesting example of building an operation using higher order building blocks. Okay, so let me write now the code for this. So here's the definition of ConcFilter. So I define it as a procedure because I need to access the output of it directly. So you see why it's important to have this kernel language ability. This lets you access things that are normally invisible. Okay, so I'm going to first call new port close, and this is L2 is going to be the stream. So the output of ConcFilter is the stream. Send close. I have to actually define them, declare them now. Send close like that. So here I've created my port with a close operation, and now I do a barrier. Barrier wants a list of procedures as input, so I'm going to create this using a map, okay, and a function like this. I do it sort of like this. So I will write this in a minute. Okay, let me first show you the skeleton of the code here, and then I will do a close. So barrier is doing a lot of work for us. Huh? It's creating a thread for each of the procedure, and it's synchronizing on all of those threads terminating. But then we also need this map because we need to construct the input argument to barrier, which is a list of procedures. So here we will return a procedure, okay, a zero argument procedure, and inside this procedure we will have the what we want to do. If f of x, then send x end. Okay, basically that's it. So this is ConcFilter. It's using the new port close and barrier. And now we can actually run it, show the example. Let me run using A and B. So let me run browse ConcFilter A2, 3, B, 5, 4, 6, whatever, like this, with a function x greater than 2. So this is now ConcFilter. Notice that there's some unbound variables here. So I run this, and okay, and it's not displaying anything, and the reason is that the barrier is waiting for the list to be terminated. Actually, I should run it like this. I think I need to run ConcFilter in its own thread. Okay. So L is equal to this. So here we get 3, 5, 4, 6. Notice that the ConcFilter itself will still wait for all things to be done. If we now bind A, if I bind A to 100, it will appear because it's greater than 2. If we bind B equal to 1, then it will not appear, but the output is nil. Notice the output now is nil because the stream is terminated. Okay? So the ConcFilter, in order to take advantage of the reduced dependencies, you have to run it in its own thread because it's also waiting for the whole list. Okay? So that's the ConcFilter. Is that it's clear how it's working? So you see we're actually using a lot higher order. We're using deterministic operations where we can, like barrier, concurrent composition, and we're using ports exactly when we need to create things without worrying about the order, because the ports, the sends can be done from many threads. So when we need to collect things, we can use port for that. And with this, we actually can build complex abstractions using a combination of deterministic data flow and ports. Okay, so let me now make a little bit conclusion on that part. Let me go back to the slides now. Okay, so now let me conclude on this part, and then after that we'll talk a little bit about Erlang. So basically, we've seen how to build. So the question is, how do you design concurrent programs? So this has been a big theme of the course up to now. And so far we have seen 3, what I consider good ways to build concurrent programs. We started by seeing deterministic data flow, including the lazy version. So this is the best way if you can use it. But of course it has limitations. If you need non-determinism, for example, if you need non-determinism to express timing requirements, then you might need to have a program be non-deterministic. Then you cannot do it in deterministic data flow. The example we showed is a client server. But deterministic data flow is widely used nowadays. Many cloud analytics tools are implicitly using this, things like Apache Flink or Spark or other tools. So this is actually a widely used paradigm nowadays. This was not true 15 years ago, but it's true today. The second approach that we saw is multi-agent programming. This is the programs when you have many agents that have to talk to each other and you have a huge amount of non-determinism. Okay, there's lots of non-determinism. And this was true for the lift example. There was a huge amount of non-determinism coming in from outside. Anyone can push buttons on any time. I can push buttons in the floors. I can push buttons in the lifts. And any time a floor or a lift can have a button pushed. So this will create messages. So there's a huge amount of non-determinism. So this is the fully general approach. But actually it's quite a bit harder to program. You cannot use functional programming techniques. We have to use the state diagram approach that we saw last time, and you have to reason about the internal state of the agents. So we have stateful agents communicating with asynchronous message, and we have to use state diagrams. So this approach works well, And I'm going to talk in a few minutes about the Erlang language. So we're going to see an introduction to Erlang in this course. And we're not going to do much Erlang programming, but I'm going to show you Erlang and show you exactly how it connects to this. Erlang is a really good example of an industrial tool that uses multi-agent programming. So that was the second one. The third one is what we saw today. This, in my view, is the best all-round way of doing concurrent programming. If you're completely free, if you're not connected to legacy requirements, then this is the approach I recommend by far as being the best. So you write most of the program as deterministic data flow as much as possible, and you add ports exactly where you need them. And usually you only need a very few ports. Okay, I've shown several examples of that. And so that's by far the best approach. You start by writing a deterministic data flow, and you only add ports when you cannot use deterministic data flow. Okay, so this, in my view, are the three good ways to build concurrent programs. After the break, we're going to see another approach, which is called shared state concurrency. This is so there's two ideas here. Monitors. So this is how languages like Java do concurrency. And then there's transactions. So this is actually quite a bit harder than the other techniques. So transactions are actually an extremely good idea. So I recommend them. Whereas monitors is a very bad idea. I will consider them as being deprecated. Unfortunately, many legacy tools are still using monitors. And so this is tools that are very old, like Java, which is already coming from 1988. So it's already 30 years old, okay? So if you have the choice, do not use this approach. But we will see it in this course. You will see this after the break. And you will understand completely why it works, but why it's not recommended. Okay? So this is the three good approaches now. Now I want to give you an introduction to Erlang before we end the course today. Erlang is a really nice system, and I even suggest you can download and try out Erlang. So I'm going to give you a practical introduction to Erlang today, which is a successful multi-agent tool for building distributed systems. So simple introduction to Erlang. So Erlang was developed by the Swedish company Ericsson, and the people developing it were a group around Joe Armstrong. And this was developed actually around the same time as Java. So Erlang and Java are about the same age. And Erlang was developed for telecommunications application. And there's a lot of history around this, a lot of interesting stories around this that I might say in some time if we have time. So there was a lot of stories of how Erlang was almost killed by Ericsson, but managed to survive and flourish because of how useful it was. So the Erlang system was released. It's called OTP, Open Telecom Platform, and it is supported by Ericsson Company today, also by an organization called the Erlang Ecosystem Foundation, and there's a large user community, and you can download the system and run it on www.erlang.org. So this you can do, and you can use it interactively and so on. So how does it work? Erlang programs consist of what they call processes. But a process is exactly a port object, as we saw. So remember the port objects, they have an internal thread, they run, and you're reading messages and executing them. So they're slightly different. There's two differences. First of all, there is no sharing. Whenever I send a message to an Erlang process, the message is copied. So the processes are completely independent. That's very important. It means if a process fails, then the other processes will not fail. Okay? So Erlang is designed for fault tolerance. So the processes are completely independent. The second point is that they don't have streams like port objects. They have a mailbox. And the difference is that you can access the mailbox by pattern matching. That means you can check whether certain kind of message is in the mailbox and take it out of the mailbox. So you can receive the messages out of order. Whereas in a port object, you have to treat the messages in order of their arrival. In Erlang, you can take the messages out of the mailbox in any order, as long as they match. Okay? So, but other than that, it's extremely close to the model we have seen. Everything that we say about multi-agent, you can do it with Erlang. And finally, Erlang has support for building distributed systems, so systems that run on networked computers, many computers communicating, that are reliable, that keep running even if there's failures, and long-lived, so that the program can keep running even though it has pieces of failure. It has invented a very interesting approach to building these systems called let it crash. So the idea is that if part of a program crashes, Erlang will not try to avoid the crash. It will encourage the crash. It will say, crash. And then another part of the program will recover. So you do not try to avoid crashes, but you recover from crashes. And it has very interesting support. It has failure linking. That means if you have two Erlang processes, and if you link them together, if one of them crashes, then automatically the system will send a message to the other one so it can recover. So the processes are linked with the failures, okay? And also you have supervisor trees. If I have a bunch of processes doing a work, I have another process on top observing all of them, which is the supervisor. That if any of the lower processes crashes, the supervisor is informed and it can do something to fix it. So this is actually very simple and extremely effective approach because of the share nothing philosophy. So you see, Erlang is really designed for these building fault-tolerant, long-lived systems. And one of the famous examples is the Ericsson AXD301 ATM switch. So ATM is a way of communicating by building virtual circuits that's used in telecommunications. So it's called asynchronous transfer mode. So AXD301 is a very high performance ATM switch. It has 1.7 million lines of Erlang code in there. It also has 1 million lines of C code for low-level stuff. And Ericsson claims, and this is something that really is making people open their eyes, availability of 99.9999999%, so 9 nines. So availability means what is the probability that when I access this system, it's running. So 99.79's availability, that is the probability that when I access the system at any time that I can actually use it, that the system is available. This turns out to be 30 milliseconds of downtime in 1 year, okay? A year which has 30 million seconds, which is very small. Over a year, only 30 milliseconds. Now, people are doubting this number. How do you measure that number? But in any case, it's extremely reliable, extremely available, okay? It's one of the most available systems because it is completely built using this Erlang philosophy. So the Erlang is a very successful way of doing this. And let me now give you a small introduction to Erlang. Let me show you some slides now on Erlang. But I go first to the chat. So is that... Okay, so we've seen the 3 ways of building, good ways of building this concurrent programs. deterministic data flow, multi-agent using port or active objects, and deterministic data flow with ports. So the third one is the best all-round way in my view. So as a teacher of a course, I have to teach you the best ways. So in my view, this is the best way. And the second way, the multi-agent, is actually very successfully used in Erlang. So there's actually a very large industrial community, and many systems, cloud systems and telecom systems, are using Erlang, especially when they have to be reliable. So let me now give you a quick introduction to Erlang using a talk coming from an Erlang company called Erlang Solutions. So this is, these slides are also on the Moodle. So this is a quick introduction to Erlang. When you see this talk, you can actually start using Erlang. So what are the important concepts in Erlang? You'll see many of the concepts you see in this course come back. There's no assignment, only pattern matching. So in fact, Erlang is a single assignment language. All variables immutable, so it's single assignment. There are case expressions with pattern matching. And also Erlang is functional. That means functions are values, like in a functional language, like we have seen. You can do higher order in Erlang. Function literals. There is no global variables. So you only have processes or port objects talking. There's no global variables. There are no statements, it's only expressions. So you're always computing functions. And Erlang uses, they call this actors. So an actor is a port object. Okay. And Erlang also calls this process. They can send and receive messages. And then there's the let it crash philosophy, where you don't try to avoid crashes, but you recover from them. So just a very quick introduction to Erlang. So there's integers, unlimited size, floats, strings in double quotes. So a string is actually a list of ASCII values. So far, it's actually very similar to Oz. This is actually very similar. It's a symbolic language. Atoms, and it has actual lists. Now, if the values in the list are ASCII values, then it's a string. It has tuples, and it has also a special value called binary, which is actually a kind of a bit vector value. So this is very useful for defining networking protocols. So you can treat binary bit vectors immediately. Okay. And now operations, arithmetic. You have integer division, remainder operation, comparison operations. Notice the funny symbols for equality and not equality. All right. You also have booleans, notice, and also an or else here. And then you have special operations for bit vectors. So Erlang is very good for building network protocols. So they have the bit vector support. You also have pattern matching in Erlang. So this actually looks very similar to what we have seen here in Oz, and also very similar to functional language. So pattern equals expression. It can be a constant, variable, or a structure. And Erlang has lists and tuples. So here, for example, this is a pattern. We have the atom OK. We have the variable stream. Notice Erlang has the same convention as Oz. The variables have uppercase and the atoms have lowercase. And actually, this is because of the historical reason, is because the first Erlang implementation, when they designed it, was implemented on top of Prolog, which has this convention. So this convention is maintained. So Erlang is a single assignment language. So basically, inside of an Erlang process, it's completely functional. We also have case statements. So you can recognize this as very similar to the case statement we have seen. Okay, we can have sequence expressions, and So here we can have multiple expressions, and we take the value of the last expression, okay, that you evaluate. And of course you have semicolon, you have funny syntax, you have to separate them by semicolons. You have if expressions. The if is interesting because it doesn't really have an else. It has what's called guards. So this is basically an if with multiple choices, and it will evaluate these guards. These are Boolean expressions. Okay. So for example, the guards are tests, type tests, Boolean operators, bitwise operators, arithmetic, relational. So here's a set of functions that you can use in guards: absolute number, head of a list, tail of a list, and then you can do other things like node, trunk, whatever. So lists now. Lists can be different type values. So again, Erlang is similar to us in that it's dynamically typed. It's a dynamically typed language, which means the type is known only at runtime. We also have in Erlang an interesting concept called a list comprehension. This is a way of defining lists that's very similar to mathematics. We have some expression, and then we have a generator. So we'll show you examples of that. So here, for example, if we have the list n, which is 1, 2, 3, 4, 5, L is 10 times x plus y, such that x is n, y is n, and x is less than y. So these are actually generators. And this will create a list according to a kind of declarative specification. So that's very interesting, and functional languages have that too. So we have list operations: head of the list, tail of the list, as usual. Okay, length of the list. And the system will show now some operations, so I'm not going to show all of them. You can create lists. Here, the sequence operation will create a list of elements 1 to 10. And there is an interactive interface. So if you download the Erlang and install the latest Erlang, which you can do by going to www.erlang.org, you can actually run this, and you will have a full functional Erlang system. And you can build very large Erlang systems already. So all these examples are using the interactive interface. So here, for example, the all operation in the list module will take a Boolean function and will check if this is true for all elements of the list. This is false, because the elements are not all even. Here, any will check if it's true for at least one element of the list. This is true. There is at least one even element in the list. And then some example of list comprehensions. But let me go just a little bit farther now. I'm not going to go to all of the detail. So the slides will show you many examples of how to run Erlang code, multiple generators, named functions. So we can define functions using patterns. Okay. We also have anonymous functions with a special syntax, and we use recursion. So this is very similar to the functional programming model we have seen. So servers, so this is the definition of a process. So this is like the loop inside of a port object. So it's like taking an element from the stream. It does something, and then it does a recursive call. So this is very similar to a port object. Notice that the recursive call is always last. So Erlang also encourages tail recursive functions. Okay. So here's an example that we saw already. Here's a factorial that is not tail recursive. So in this slide, you see that you have to put the multiplications on the stack here. And if the stack is too deep, it will crash. It will go too deep. So the idea is to use tail recursion, because tail recursion is like a while loop. You can see that it's explaining that here. Tail recursion, you never run out of stack space. So you can see that Erlang uses a very similar philosophy to what we've seen in this course. There's a simple trick for making functions tail recursive, they say, with accumulators. This seems very familiar to us, okay? So here's a version of factorial using an accumulating parameter, and then it turns into a while loop, okay? There is actually a web book called Learn You Some Erlang for Great Good, which I highly recommend if you want to become a proficient Erlang programmer. So this is available on the web for free. So you can look at that, Learn You Some Erlang for Great Good. There's also I/O, so I'm not going to go to all of the details since we're almost done here. Just want to go, you can of course do file I/O. So here's an example. So in Erlang you basically create modules and you export things. This module defines a simple function and you can call it in the interactive interface. Now let's look at messages. Okay, message passing. So Erlang has no global variables. It's only processes or port objects sending messages. There's no global variables, okay? Because global variables is bad. It's a major source of error. So the Erlang philosophy is no global variables. Concurrency is done by passes messages between what they call actors, which is a very lightweight process. So to create a new process, like new port object, Erlang has a function called spawn, and you give it the state transition function. Basically, the function might be anonymous. So a simple example of this, so the send operation is an exclamation point called bang. So let me show you an example of this very quickly. So receive is a mailbox. So it basically, you do receive and it will automatically take a message that matches from the pattern or block if it does not. Each process has a mailbox especially attached to it. So this is corresponding to the stream. If the mailbox is empty, it will block. If it is not empty, it will find the first pattern that matches. If it finds none, it blocks. Okay. If no pattern matches, it will block waiting. Okay. So here is finally a simple process. So here we have a loop that receives two different kinds of messages. So these are tuples. This is a tuple. Rectangle, width, height. So rectangle is an atom. Width, height are variables. And it will print area of rectangle is width times height. And the other one is this. And if it receives anything else, so this is like an else, it will say, I don't know, because the variable matches everything. So here we actually spawn an area server with this function, and here we send it a message. So here we have actually created the server. Okay, let me stop here because it's 10:30. Okay, I'll talk a little bit more about Erlang after the break. So also you're going to be receiving the project. Soon you're going to be receiving the project. I have to talk to the... Okay. Okay, so I'm going to end the course for today. I see there's one question. The question is related to the previous slide on slide 23 on the port, the close for the port object. Is the nil equal PC? So PC, I struggle a bit to understand the nil equal read PC. Is this equivalent to read PC colon equal nil? No, it's not the same. So actually PC is a cell, and at PC is the value of the cell, which is the end of the stream. It's an unbound variable. Okay, so if we doing PC equal nil, we'll bind the end of the stream. We'll bind this variable, but will not change the content of the cell. So the cell still contains this bound variable. But doing PC colon equal nil will change the content of the cell. It will not bind the variable, which was the old content. Okay, so basically the cell contains a variable. It's a box. It contains a variable. If I do at PC equal nil, I will access this variable and bind it. But the box will still have the same variable. It still contain this variable. So variable will be bound. So, but the box is still containing this bound variable. So I'm not changing the content. But if I do colon equal, this changes the content of the box. Okay? It doesn't bind any variables. It only changes the content of the box. So the box, which used to have a variable, now contains nil. But the variable is still in memory somewhere. It's just the box no longer references that variable. Okay? So the two operations are completely different. If I do read PC equal nil, I'm binding the variable but not changing the content of the box. Where if I do PC colon equal nil, I'm changing the content of the box, but I'm not binding the variable. Okay? I hope. Does it make it clearer? Okay, very good. So the course is now done. It's now 10:30 already. I will stick around a little to answer questions if people have questions. Thank you very much, and have a good rest of week and Easter vacation.